I've been working with my CCNA for several years now, and I come to realize that when I was studying, one of the topics that was really hard for me was STP. And it's like one of those subjects in high school to me, like geometry. Do you need to know geometry to pass your high school diploma? Yes, but are you going to use it in like your day-to-day life? Not normally. And I feel STP is the same way. It's kind of running on by default, and you never really come across any issues with it. Either way, you do need to know it to pass the CCNA. That's why I wanted to put this lab together for y'all to hopefully just break down this topic in a simple and easy to understand kind of format for you. Now, there's going to be three key things that I believe everybody should know to get a real grasp and understanding of protocol. So number one, you're going to need to understand that root bridge election process. The number two thing is understanding the root port election process on all the non-root bridges. And then you're going to have to understand the designated port and its role and how it gets elected on network segments. And we'll be going over all of that in the lab. Try to stick around to the end where I'm going to be going over one of the tiebreakers in these election processes that I don't think makes much sense, and I don't think it could work possibly. And maybe you can help me out with that. All right, so here we got the lab set up. It's just 4 switches that we got here. We got their interfaces and a lot of stuff going on. Hopefully you guys can see everything. But we got DP here for designated port, designated port. We got a root port. We got a port that's blocking. We got another root port, another designated port, and a blocking port. So the first thing we want to look at is the root switch and that election process, or the root bridge election process. All right, now I'm logged into the root switch. Number one, to verify that I'm in the root switch, you can use the show spanning tree command. This command will show you literally that this bridge is the root. That's the first thing to look for. Now, how did this bridge become the root bridge? Another way that you can verify that this bridge is the root, if you happen to miss that, or if they don't provide that on the test, is every root bridge has all of its ports roles as designated ports. So as you can see, for this root bridge, you can see all the ports are designated, and that's how it should go. There's no blocking ports on a root bridge, or no alternate ports or anything like that. Everything is forwarding and designated for a root bridge. Now that we know that and verify that this is the root bridge, how did this become the root bridge? Well, there's an election process that takes place, and the election process looks at the bridge ID, which is right here. And the bridge ID is made up of your priority, your bridge priority, and the MAC address. This is the MAC address of the switch right here. So these two values combined give you the value of your bridge ID. Now, when all of these switches came online in the topology, they all shared that information, their MAC address and their bridge ID. Let's log into this non-root switch and look at its bridge ID for comparison. Now we're logged into the non-root switch. Let's look at the output from show spanning tree here. As you can see, we have the bridge ID here, but this bridge is not the root. There's no information. Also, we see blocking ports. That's also a good indication that you're not in the root bridge. Now, the bridge ID is made up of the priority and the MAC address. All right, I've pulled up the root bridge here so that we could look at the bridge IDs in comparison. So the bridge ID for the root bridge, again, is made up of the priority, and the default priority is 32,768. However, you have to add this system ID extension, which is the VLAN that we're a part of, which is VLAN 1 up here. So that's where we're getting the 32,769. But basically, all the switches are using the same priority for their bridge ID. So if you're using the same priority for your bridge ID, then those tie for all of our switches in the topology. So for the election, to break that tie, we have to use the rest of the bridge ID, which is the MAC address. And the MAC address here for the bridge, for the root bridge, is 0004. This MAC address is lower than 00D0. Therefore, the bridge ID on this switch is lower than the bridge ID on this switch. Therefore, this switch becomes the root bridge between these two switches. Now, this same election process and logic happened throughout all these other switches here. And everybody converged and agreed that, hey, this guy, even though we all have the same priority of 32,769 in our bridge IDs, the MAC address was the lowest on this guy. So we all bow down and we'll let him be King Kong, right? That's the root switch. So we all answer to him. All right. After we've determined that we have the root bridge right here and we have the non-root bridges, the next election process we have to look at is the root port election process. So how did, out of FA01 and FA02, this switch decide that, hey, you're going to be the root port for this switch? The root port is the lowest cost port to reach the root switch. What that means is each port has a cost to reach the root switch. And these are all default according to the links that they're using. If you're using a fast Ethernet link, the cost to reach the root switch for you is 19. If you're using a gigabit link, the cost to reach the root switch would be the cost of 4. So let's look at the cost to reach the root switch for FA02. So FA02, for this port FA02 to reach this switch, he uses one fast Ethernet link. That cost is 19. Now, FA01, the port on this side, to reach that same root switch, he would have to use the cost of this Ethernet segment, they call it, or this link, is just another name for segment, which is 19, as well as the gig to gig 01 link right here, which is a cost of 4. So that would be a total cost of 23. So the switch says it'll cost me 23 to reach the root switch, or I could take 19, and it uses the lower cost, and that's how that's determined. Now, if the cost is tied for both of these, the next tiebreaker will be the actual interface number. So if the costs were the same for both of these links, if it was 19 here and 19 here to reach it, it would use port 1. If the cost was the same for this link and this link to reach the root switch, it would use the lower physical port number, so that would be 1. But that's not the case. The cost to reach the root switch is 19 here, and it's 23 here. Again, 19 for this link, and then you get charged another cost of 4 for this link between these two switches up here to reach that root switch, which is 23. So that's how that became the root port on that switch. Now, the same thing happened on this switch. However, we got a designated port on this switch, and on this switch, there was not a designated port. It was just a blocking port. Let's take a little closer look of why this port came up as a designated port, because we know why this port became the root port. Just like I said before, there's a cost to reach the root switch from this non-root bridge, and the cost out of a gig 02 link is the cost of 4. Now the cost for this guy would be the cost of 19 for his fast Ethernet link, and then a cost of 4 for this gig link, which would be at 23. Since this link is 4, that's less than 23, this becomes the root port. Now, that leads me to the designated port election process, which happens between two switches on a network segment. Now, how did this device become elected the designated port? Well, we have to look at the costs again, because the lower the cost is going to be the one that wins the election of that port. Now, this switch's cost to reach the root port is 4. We already see that. So he tells them it costs me 4 to get to the root switch. So he says, how much does it cost? He's asking this port FA03, how much does it cost your switch to reach the root switch? Well, this one returns his information and says, well, I'm on a gig link too. It costs me 4. So now if the costs tie, the next tiebreaker is going to be the bridge ID. So again, we need to look at the bridge ID of this guy and this guy. And the bridge ID is going to win the election. All right, the top switch, his bridge ID is right here. So we know the priorities are all the same, but the MAC address is 0060. This MAC address for the bottom switch is 0030. So on this network segment, the designated port is going to elect the switch with the lowest bridge ID, which is going to be this bottom switch. And that's why he becomes the designated port and he has to move into the blocking state. So now the same thing on this link from here to here. Now it's a little different why this is the designated port for this network segment than it is with this designated port. So let's look at the logic for why this got elected as the designated port. So on this link from FA01 to FA01, this switch says that it costs me my FA link or my fast Ethernet link, which is a 100 meg link, that costs me 19 to get to the root switch. Then he asks him, how much does it cost you? Well, he looks at his root port to that root switch, and his cost for his link is a gig link, which is only 4. So he says, it only costs me 4. It costs you 19. You go in the blocking state. I'll become the designated port for this segment. Then once he becomes the designated port, this port has to go into the blocking state. And now we have a loop-free topology with both of these links being blocked. There's going to be only one path to get back to the root switch, even though we have all these redundant links. I hope all y'all found some kind of value in it. Hopefully I made sense and I broke it down pretty easily for you to understand. And just to summarize, you just got to know the root bridge election process, the root port election process on the non-root bridges, and then that designated port election process on those network segments. Once you get all of that, you'll definitely be able to get a good handle on STP. Oh yeah, and that tiebreaker that I was talking about at the beginning of the video, one of the tiebreakers is if the bridge IDs, if those tie, then they move down to another tiebreaker. However, we already know that the bridge IDs, for those to tie, the bridge ID has to have the same bridge priority, which is okay, but they also have to have the same MAC address for that tie to happen and a tiebreaker to take place. The whole point of a MAC address, from my understanding, is that it's unique and that there's only one of them in the world. So how in the world can you have two of the same MAC addresses? Either way, if you ever come across two MAC addresses in the STP environment, just know that that's going to be a tiebreaker for your root port. Again, I appreciate each and every one of y'all ninjas. And make sure to like and comment, subscribe, so you can see more videos like this. And it really helps out the channel. Appreciate y'all, and I'm going to holler at y'all in the next video.